lines should just call flash attention in this exact way. We have to do it again for it, which in my opinion is a little bit odd, but here we are. So you have to use this compound up, and let's wait for a few moments before torch compile gets around to it. And then let's remember that we achieved 6.05661. I have it here. That's the loss we were expecting to see. And we took 130 milliseconds before this change. So we're expecting to see the exact same result by iteration 49, but we expect to see faster runtime because flash attention is just an algorithmic rewrite and it's a faster kernel, but it doesn't actually change any of the computation, and we should have the exact same optimization. So, okay, so we're a lot faster. We're at about 95 milliseconds, and we achieved 6.058. Okay, so they're basically identical up to a floating point fudge factor. So it's the identical computation, but it's significantly faster, going from 130 to roughly 96. And so this is 96 divide 130-ish. So this is maybe 27-ish% improvement. Really interesting, and that is flash attention. Okay, we are now getting to one of my favorite optimizations, and it is simultaneously the dumbest and the most brilliant optimization, and it's always a little bit surprising to me. Anyway, so basically I mentioned a few minutes ago that there are some numbers that are nice and some numbers that are ugly. So 64 is a beautiful, nice number. 128 is even nicer. 256 is beautiful. What makes these numbers beautiful is that there are many powers of 2 inside them. You can divide by 2 many times. And examples of ugly numbers are like 13 and 17 and something like that. Prime numbers, numbers that are not even, and so on. And so pretty much you always want to use nice numbers in all of your code that deals with neural networks or CUDA, because everything in CUDA works in sort of like powers of 2, and lots of kernels are written in terms of powers of 2, and there are lots of blocks of sizes 16 and 64 and so on. So everything is written in those terms, and you always have special case handling for all kinds of logic that when your inputs are not made of nice numbers. So let's see what that looks like. Basically, scan your code and look for ugly numbers is roughly the heuristic. So 3 times is kind of ugly. I'm not 100% sure. Maybe this can be improved, but this is ugly and not ideal. 4 times is nice, so that's nice. 1024 is very nice. That's a power of 2. 12 is a little bit suspicious. Not too many powers of 2. 768 is great. 50,000 to 57 is a really, really ugly number. It's, first of all, it's odd. So and there's not too many powers of 2 in there. So this is a very ugly number, and it's highly suspicious. And then when we scroll down, all these numbers are nice. And then here we have mostly nice numbers except for 25. So in this configuration of GPT-2 XL, the number of heads is 25. That's a really ugly number. That's an odd number. And actually, this did cause a lot of headaches for us recently when we were trying to optimize some kernels to run this fast, and required a bunch of special case handling. So basically, these numbers are, we have some ugly numbers, and some of them are easier to fix than others. And in particular, the vocab size being 50,000 to 57, that's a very ugly number, very suspicious, and we're going to fix it. Now, when you fix these things, one of the easy ways to do that is you basically increase the number until it's the nearest power of 2 that you like. So here's a much nicer number. It's 50,304. And why is that? Because 50,304 can be divided by 8 or by 16 or by 32, 64. It can even be divided by 128, I think. Yeah. So it's a very nice number. So what we're going to do here is, this is the GPT config, and you see that we initialize vocab size to 50,257. Let's override just that element to be 50,304. Okay. So everything else stays the same. We're just increasing our vocabulary size. So we're adding, it's almost like we're adding fake tokens. So that vocab size has powers of 2 inside it. Now, actually what I'm doing here, by the way, is I'm increasing the amount of computation that our network will be doing. If you just count the flops on, like, do the math of how many flops we're doing, we're going to be doing more flops. And we still have to think through whether this doesn't break anything. But if I just run this, let's see what we get. Currently, this ran in maybe 96.5 milliseconds per step. I'm just kind of like eyeballing it. And let's see what kind of a result we're going to get. While this is compiling, let's think through whether our code actually works okay when we increase the vocab size like this. Let's look at where vocab size is actually used. So we swing up to the init, and we see that it's used inside the embedding table, of course, so all the way at the bottom of the transformer, and it's used at the classifier layer, all the way at the top of the transformer, so in two places. And let's take a look, and we're running at 93. So 93 milliseconds instead of 96.5. So we are seeing a roughly 4% improvement here by doing more calculations. And the reason for this is we've made an ugly number into a nice number. I'm going to come into the explanation for that a little bit again, but for now, let's just convince ourselves that we're not breaking anything when we do this. So first of all, we've made the WTE, the embedding table for the tokens, we've made it larger. It's almost like we introduced more tokens at the bottom. And these tokens are never used because the GPT tokenizer only has tokens up to 50,256. And so we'll never index into the rows that we've added. So we're wasting a little bit of space here by creating memory that's never going to be accessed, never going to be used, etc. Now that's not fully correct because this WTE weight ends up being shared and ends up being used in the classifier here at the end. So what is that doing to the classifier right here? Well, what that's doing is we're predicting additional dimensions at the classifier now, and we're predicting probabilities for tokens that will, of course, never be present in the training set. And so therefore, the network has to learn that these probabilities have to be driven to 0. And so the logits that the network produces have to drive those dimensions of the output to negative infinity. But that's no different from all the other tokens that are already in our dataset, or rather that are not in our dataset. So Shakespeare only probably uses, let's say, 1,000 tokens out of 50,257 tokens. So most of the tokens are already being driven to 0 probability by the optimization. We've just introduced a few more tokens now that in a similar manner will never be used and have to be driven to 0 in probability. So functionally, though, nothing breaks. We're using a bit more extra memory, but otherwise this is a harmless operation as far as I can tell. And we're adding calculation, but it's running faster. And it's running faster because, as I mentioned in CUDA, so many kernels use block tiles, and these block tiles are usually nice numbers, so powers of 2. So calculations are done in like chunks of 64 or chunks of 32. And when your desired calculation doesn't neatly fit into those block tiles, there are all kinds of boundary kernels that can kick in to like do the last part. So basically, in a lot of kernels, they will truncate up your input and they will do the nice part first, and then they have a whole second phase where they come back to anything that remains, and then they process the remaining part. And the kernels for that could be very inefficient. And so you're basically spinning up all this extra compute, and it's extremely inefficient. So you might as well pad your inputs and make it fit nicely. And usually that empirically ends up actually running faster. So this is another example of a 4% improvement that we've added. And this is something that also Torch Compile did not find for us. You would hope that Torch Compile at some point could figure an optimization like this out. But for now, this is it. And I also have to point out that we're using PyTorch nightly. So that's why we're only seeing 4%. If you're using PyTorch 2.3.1 or earlier, you would actually see something like 30% improvement just from this change, from changing it to from 50,257 to 5304. So again, one of my favorite examples also of having to understand the under the hood and how it all works, and to know what kinds of things to tinker with to push the performance of your code. Okay, so at this point we have improved the performance by about 11x, right? Because we started at about 1,000 milliseconds per step, and we're now down to like 93 milliseconds. So that's quite good, and we're doing a much better job of utilizing our GPU resources. So I'm going to now turn to more algorithmic changes and improvements to the actual optimization itself. And what we would like to do is we would like to follow the hyperparameters that are mentioned in the GPT-2 or GPT-3 paper. Now, sadly, GPT-2 doesn't actually say too much. It's very nice of them that they released the model weights and the code, but the paper itself is extremely vague as to the optimization details. The code itself that they released as well, the code we've been looking at, this is just the inference code. So there's no training code here and very few hyperparameters. So this doesn't also tell us too much. So for that, we have to turn to the GPT-3 paper. And in the appendix of the GPT-3 paper, they have a lot more hyperparameters here for us to use. And the GPT-3 paper in general is a lot more detailed as to all of the small details that go into the model training, but GPT-3 models were never released. So GPT-2, we have the weights, but no details, and GPT-3, we have lots of details, but no weights. So, but roughly speaking, GPT-2 and GPT-3 architectures are very, very similar. And basically, there are very few changes. The context length was expanded from 1024 to 2048, and that's kind of like the major change. And some of the hyperparameters around the transformer have changed. But otherwise, they're pretty much the same model. It's just that GPT-3 was trained for a lot longer on a bigger data set and has a lot more thorough evaluations. And the GPT-3 model is 175 billion instead of 1.6 billion in the GPT-2. So long story short, we're going to go to GPT-3 paper to follow along some of the hyperparameters. So to train all the versions of GPT-3, we use Atom with beta 1, beta 2 of 0.9 and 0.95. So let's swing over here and make sure that the betas parameter, which you can see here defaults to 0.9 and 0.999, is actually set to 0.9 and 0.95. And then the epsilon parameter, you can see is the default is 1 e negative 8, and this is also 1 e negative 8. Let's just put it in so that we're explicit. Now, next up, they say we clip the global norm of the gradient at 1.0. So what this is referring to is that once we calculate the gradients right after loss.backward, we basically have the gradients at all the parameter tensors. And what people like to do is basically clip them to have some kind of a maximum norm. So in PyTorch, this is fairly easy to do. It's one line of code here that we have to insert right after we calculate the gradients. And what this utility function is doing is it's calculating the global norm of the parameters. So every single gradient on all the parameters, you square it and you add it all up and you take a big square root of that. And that's the norm of the parameter vector, basically. It's the length of it, if you'd like to look at it that way. And we are basically making sure that its length is no more than 1.0, and we're going to clip it. And the reason that people like to use this is that sometimes you can get unlucky during the optimization. Maybe it's a bad data batch or something like that. And if you get very unlucky in the batch, you might get really high loss, and really high loss could lead to a really high gradient. And this could basically shock your model and shock the optimization. So people like to use gradient norm clipping to prevent the model from basically getting too big of shocks in terms of the gradient magnitude, and they upper bound it in this way. It's a bit of a hacky solution. It's about like a patch on top of like deeper issues, but people still do it fairly frequently. Now, the clip grad norm returns the norm of the gradient, which I like to always visualize because it is useful information, and sometimes you can look at the norm of the gradient, and if it's well behaved, things are good. If it's climbing, things are bad and they're destabilizing during training. Sometimes you could get a spike in the norm, and that means there's some kind of an issue or an instability. So the norm here will be a norm, and let's do a 0.4f or something like that. And I believe this is just a float. And so we should be able to print that. So that's global gradient clipping. Now they go into the details of the learning rate scheduler. So they don't just use a fixed learning rate like we do here for 3e negative 4, but there's actually basically a cosine decay learning rate schedule. It's got a warm-up, and it's got a cosine decay to 10% over some horizon. And so we're gonna implement this in a second. I'd just like to see the norm printed here. Okay, there we go. So what happened here is the norm is actually really high in the beginning, 30 or so. And you see that as we continue training, it kind of like stabilizes at values below 1. And this is not that crazy uncommon for the norm to be high in the very first few stages. Basically what's happening here is the model is completely random, and so there's a ton of learning happening very early in the network, but that learning is kind of like, it's mostly learning the biases of the output tokens, and so it's a bit of an unstable time, but the network usually stabilizes in a very few iterations. So this looks relatively reasonable to me, except usually I would expect, this looks a little bit funky, that we go from 28 to 6 to 2 and then to 10. It's not completely insane, but it's just kind of a little bit funky. Okay, so let's now get to the learning rate scheduler. So the learning rate schedule that's used here in GPT-3 is what's called a cosine decay learning schedule with warm-up. And the way this looks is that the learning rate is basically starts right at around 0, linearly ramps up over some amount of time, and then comes down with this cosine sort of form and comes down to some kind of a minimum learning rate that's up to you. So here the minimum learning rate is 0, but here in the paper, they said that they use cosine decay for learning rate down to 10% of its value over the first 260 billion tokens, and then training continues 10% after. And there's a linear warm-up over the first 375 million tokens. So that's about the learning rate. So let's now implement this. So I already implemented it here. And the way this works is, let me scroll down first here. I changed our training loop a little bit. So this was a 4i in max steps. I just changed it to step now, so that we have the notion of a step is a single optimization step in the for loop. And then here, I get the LR for this step of the optimization using a new function I call getLR. And then in PyTorch, to set the learning rate, I think this is the way to set the learning rate. It's a little bit gnarly because you have to, basically there's a notion of different parameter groups that could exist in the optimizer. And so you actually have to iterate over them, even though we currently have a single param group only. And you have to set the LR in this for loop kind of style is my impression right now. So we have this local LR, we set the learning rate, and then on the bottom, I'm also printing it. So that's all the changes I made to this loop. And then of course the getLR is my scheduler. Now it's worth pointing out that PyTorch actually has learning rate schedulers, and you can use them. And I believe there's a cosine learning rate schedule in PyTorch. I just don't really love using that code because honestly, it's like 5 lines of code, and I fully understand what's happening inside these lines, so I don't love to use abstractions where they're kind of inscrutable and then I don't know what they're doing, so personal style. So the max learning rate here is, let's say 3e-4, but we're going to see that in GPT-3 here, they have a table of what the maximum learning rate is for every model size. So for this one, basically 12 layer 768 GPT-3. So the GPT-3 small is roughly like a GPT-2 124M. We see that here they use a learning rate of 6e-4. So we could actually go higher. In fact, we may want to try to follow that and just set the max LR here at 6. Then that's the maximum learning rate. The min learning rate is 10% of that per description in the paper. Some number of steps that we're going to warm up over, and then the maximum steps of the optimization, which I now use also in the for loop down here. And then you can go over this code if you like. It's not terribly insightful or interesting. I'm just modulating based on the iteration number which learning rate there should be. So this is the warm-up region. This is the region after the optimization, and then this is the region sort of in between. And this is where I calculate the cosine learning rate schedule. And you can step through this in detail if you'd like. But this is basically implementing this curve. And I ran this already, and this is what that looks like. So when we now run, we start at some very low number. Now note that we don't start exactly at 0, because that would be not useful to update with a learning rate of 0. That's why there's an it plus 1, so that on the 0th iteration, we are not using exactly 0, we're using something very, very low. Then we linearly warm up to maximum learning rate, which in this case was 3e-4 when I ran it, but now would be 6e-4. And then it starts to decay all the way down to 3e-5, which was at the time 10% of the original learning rate. Now, one thing we are not following exactly is that they mentioned that, let me see if I can find it again. We're not exactly following what they did because they mentioned that their training horizon is 300 billion tokens, and they come down to 10% of the initial learning rate at 260 billion, and then they train after 260 with 10%. So basically their decay time is less than the max steps time, whereas for us they're exactly equal. So it's not exactly faithful, but it's an okay, this is okay for us and for our purposes right now. And we're just going to use this ourselves. I don't think it makes too big of a difference, honestly. I should point out that what learning rate schedule you use is totally up to you. There's many different types. Cosine learning rate has been popularized a lot by GPT-2 and GPT-3, but people have come up with all kinds of other learning rate schedules. And this is kind of like an active area of research as to which one is the most effective at training these networks. Okay, next up, the paper talks about the gradual batch size increase. So there's a ramp on the batch size that is linear, and you start with very small batch size and you ramp up to a big batch size over time. We're going to actually skip this and we're not going to work with it. And the reason I don't love to use it is that it complicates a lot of the arithmetic because you are changing the number of tokens that you're processing at every single step of the optimization. And I like to keep that math very, very simple. Also, my understanding is that this is not like a major improvement. And also my understanding is that this is not like an algorithmic optimization improvement. It's more of a systems and speed improvement. And roughly speaking, this is because in the early stages of the optimization, again, the model is in a very atypical setting. And mostly what you're learning is that you're mostly learning to ignore the tokens that don't come up in your training set very often. You're learning very simple biases and that kind of a thing. And so every single example that you put through your network is basically just telling you use these tokens and don't use these tokens. And so the gradients from every single example are actually extremely highly correlated. They all look roughly the same in the original parts of the optimization, because they're all just telling you that these tokens don't appear and these tokens do appear. And so because the gradients are all very similar and they're highly correlated, then why are you doing batch sizes of like millions when if you do a batch size of 32K, you're basically getting the exact same gradient early on in the training. And then later in the optimization, once you've learned all the simple stuff, that's where the actual work starts. And that's where the gradients become more decorrelated per examples. And that's where they actually offer you sort of statistical power in some sense. So we're going to skip this just because it kind of complicates things. And we're going to go to data are sampled without replacement during training. So until an epoch boundary is reached. So without replacement means that they're not sampling from some fixed pool and then take a sequence, train on it, but then also like return the sequence to the pool. They are exhausting a pool. So when they draw a sequence, it's gone until the next epoch of training. So we're already doing that because our data loader iterates over chunks of data. So there's no replacement. They don't become eligible to be drawn again until the next epoch. So we're basically already doing that. All models use a weight decay of 0.1 to provide a small amount of regularization. So let's implement the weight decay. And you see here that I've already kind of made the changes. And in particular, instead of creating the optimizer right here, I'm creating a new configure optimizers function inside the model, and I'm passing in some of the hyperparameters instead. So let's look at the configure optimizers, which is supposed to return the optimizer object. Okay, so it looks complicated, but it's actually really simple, and it's just we're just being very careful, and there's a few settings here to go through. The most important thing with respect to this line is that you see there's a weight decay parameter here, and I'm passing that into I'm passing that into something called optim groups that eventually ends up going into the add and W optimizer. And the weight decay that's by default used in add and W here is 0.01, so it's 10 times lower than what's used in the GPT-3 paper here. So the weight decay basically ends up making its way into the add and W through the optimizer groups. Now, what else is going on here in this function? So the two things that are happening here that are important is that I'm splitting up the parameters into those that should be weight decayed and those that should not be weight decayed. So in particular, it is common to not weight decay biases and any other sort of one-dimensional tensors. So the one-dimensional tensors are in the no decay params, And these are also things like layer norm, scales, and biases. It doesn't really make sense to weight decay those. You mostly want to weight decay the weights that participate in matrix multiplications, and you want to potentially weight decay the embeddings. And we've covered in previous video why it makes sense to decay the weights, because you can sort of think of it as a regularization, because when you're pulling down all the weights, you're forcing the optimization to use more of the weights, and you're not allowing any one of the weights individually to be way too large. You're forcing the network to kind of like distribute the work across more channels, because there's sort of like a pull of gravity on the weights themselves. So that's why we are separating it in those ways here. We're only decaying the embeddings and the matmul participating weights. We're printing the number of parameters that we're decaying and not. Most of the parameters will be decayed. And then one more thing that we're doing here is I'm doing another optimization here. And previous AtomW did not have this option, but later parts of PyTorch introduced it. And that's why I'm guarding it with an inspect.signature, which is basically checking if this fused quark is present inside AtomW. And then if it is present, I'm gonna end up using it and passing it in here, because some earlier versions do not have fused equals. So here's AtomW, fused equals. It did not used to exist, and it was added later. And there's some docs here for what's happening. And basically they say that by default they do not use fused because it is relatively new and we want to give it sufficient bake time. So by default they don't use fused, but fused is a lot faster when it is available and when you're running on CUDA. And what that does is, instead of iterating in a for loop over all the parameter tensors and updating them, that would launch a lot of kernels, right? And so fused just means that it's all those kernels are fused into a single kernel. You get rid of a lot of overhead, and you a single time on all the parameters call a kernel that updates them. And so it's just basically a kernel fusion for the AtomW update instead of iterating over all the tensors. So that's the configure optimizers function that I like to use, and we can rerun. And we're not going to see any major differences from what we saw before, but we are going to see some prints coming from here. So let's just take a look at what they look like. So we see that number of decayed tensors is 50, and it's most of the parameters, and number of non-decayed tensors is 98, and these are the biases and the layer norm parameters mostly, and there's only 100,000 of those. So most of it is decayed, and then we are using the fused implementation of AtomW, which will be a lot faster. So if you have it available, I would advise you to use it. I'm not actually 100% sure why they don't default to it. It seems fairly benign and harmless. And also because we are using the fused implementation, I think this is why we have dropped. Notice that the running time used to be 93 milliseconds per step, and we're now down to 90 milliseconds per step because of using the fused AtomW optimizer. So in a single commit here, we are introducing fused atom, getting improvements on the time, and we're changing the weight decay, but we're only weight decaying the two-dimensional parameters, the embeddings, and the matrices that participate in linear. So that is this, and we can take this out. And yeah, that is it for this line. One more quick note before we continue here. I just want to point out that the relationship between weight decay, learning rate, batch size, the atom parameters, beta 1, beta 2, the epsilon, and so on, these are very complicated mathematical relationships in the optimization literature. And for the most part, in this video, I'm just trying to copy paste the settings that OpenAI used, but this is a complicated topic, quite deep. And yeah, in this video, I just want to copy the parameters because it's a whole different video to really talk about that in detail and give it a proper justice instead of just high-level intuitions. Now, the next thing that I want to move on to is that this paragraph here, by the way, we're going to turn back around to when we improve our data loader. For now, I want to swing back around to this table where you will notice that for different models, we of course have different hyperparameters for the transformer that dictate the size of the transformer network. We also have a different learning rate. So we're seeing the pattern that the bigger networks are trained with slightly lower learning rates. And we also see this batch size where in the small networks, they use a smaller batch size, and in the bigger networks, they use a bigger batch size. Now, the problem for us is we can't just use 0.5 million batch size, because if I just try to come in here and I try to set this B, where's my B? B equals, where do I call the data? Okay, B equals 16. If I try to set, well, we have to be careful. It's not 0.5 million because this is the batch size in the number of tokens. Every single one of our rows is 1024 tokens. So 0.5 E6, 1 million divided 1024. This would need about a 488 batch size. So the problem is I can't come in here and set this to 488 because my GPU would explode. This would not fit for sure. And so, but we still want to use this batch size because, again, as I mentioned, the batch size is correlated with all the other optimization hyperparameters and the learning rates and so on. So we want to have a faithful representation of all the hyperparameters, and therefore we need to use a batch size of 0.5 million roughly. But the question is, how do we use 0.5 million if we only have a small GPU? Well, for that, we need to use what's called gradient accumulation. So we're going to turn to that next, and it allows us to simulate in a serial way any arbitrary batch size that we set. And so we can do a batch size of 0.5 million, we just have to run longer, and we have to process multiple sequences and basically add up all the gradients from them to simulate a batch size of 0.5 million. So let's turn to that next. Okay, so I started the implementation right here just by adding these lines of code. And basically what I did is first I set the total batch size that we desire. So this is exactly 0.5 million, and I used a nice number, a power of 2, because 2 to the 19 is 524,288. So it's roughly 0.5 million, and it's a nice number. Now, our micro batch size, as we call it now, is 16. So this is going to be, we still have B by T indices that go into the transformer and do forward, backward, but we're not going to do an update, right? We're going to do many forward, backwards. And those gradients are all going to plus equals on the parameter gradients. They're all going to add up. So we're going to do forward, backward, grad, accum steps number of times. And then we're going to do a single update once all of that is accumulated. So in particular, our micro batch size is just now controlling how many tokens, how many rows we're processing in a single go of a forward, backward. So here we are doing 16 times 124. We're doing 16,384 tokens per forward, backward. And we are supposed to be doing 2 to the 19. Whoops, what am I doing? 2 to the 19 in total. So the grad accum will be 32. So therefore, grad accum here will work out to 32. And we have to do 32 forward, backward, and then a single update. Now, we see that we have about 100 milliseconds for a single forward, backward. So doing 32 of them will make every step roughly 3 seconds, just napkin math. So that's grad accum steps, but now we actually have to implement that. So we're going to swing over to our training loop, because now this part here and this part here, the forward and the backward, we have to now repeat this 32 times before we do everything else that follows. So let's see how we can implement that. So let's come over here, and actually we do have to load a new batch every single time. So let me move that over here. And now this is where we have the inner loop. So for micro step in range grad accum steps, we do this. And remember that loss.backward always deposits gradients. So we're doing inside loss.backward, there's always a plus equals on the gradients. So in every single loss.backward, gradients will add up on the gradient tensors. So we loss.backward, and then we get all the gradients over there, and then we normalize, and everything else should just follow. So we're very close, but actually there's like subtle and deep issue here, and this is actually incorrect. So I invite you to think about why this is not yet sufficient, and let me fix it then. Okay, so I brought back the Jupyter notebook so we can think about this carefully in a simple toy setting and see what's happening. So let's create a very simple neural net that takes a 16 vector of 16 numbers and returns a single number. And then here I'm creating some random examples x and some targets y. And then we are using the mean squared loss here to calculate the loss. So basically what this is 4 individual examples, and we're just doing simple regression with the mean squared loss over those 4 examples. Now, when we calculate the loss and we loss that backward and look at the gradient, this is the gradient that we achieve. Now, the loss objective here, notice that in MSE loss, the default for the loss function is reduction is mean. So we're calculating the average mean loss, the mean loss here over the 4 examples. So this is the exact loss objective, and this is the average, the 1/4, because there are 4 independent examples here. And then we have the 4 examples and their mean squared error, the squared error, and then this makes it the mean squared error. So therefore, we calculate the squared error and then we normalize it to make it the mean over the examples. And there's 4 examples here. So now when we come to the gradient accumulation version of it, this here is the gradient accumulation version of it, where we have grad accum steps of 4, and I reset the gradient. With grad accum steps of 4, and now I'm evaluating all the examples individually instead and calling loss that backward on them many times. And then we're looking at the gradient that we achieve from that. So basically now we forward our function, calculate the exact same loss, do a backward, and we do that 4 times. And when we look at the gradient, you'll notice that the gradients don't match. So here we did a single batch of 4, and here we did 4 gradient accumulation steps of batch size 1. And the gradients are not the same. And basically the reason that they're not the same is exactly because this mean squared error gets lost. This 1/4 in this loss gets lost, because what happens here is the loss objective for every one of the loops is just a mean squared error, which in this case, because there's only a single example, is just this term here. So that was the loss in the 0th iteration, the same in the 1st, 3rd, and so on. And then when you do the loss dot backward, we're accumulating gradients. And what happens is that accumulation in the gradient is basically equivalent to doing a sum in the loss. So our loss actually here is this without the factor of 1/4 outside of it. So we're missing the normalizer, and therefore our gradients are off. And so the way to fix this, or one of them, is basically we can actually come here and we can say loss equals loss divide 4. And what happens now is that we're scaling our loss. We're introducing a 1/4 in front of all of these places. So all the individual losses are now scaled by 1/4. And then when we backward, all of these accumulate with a sum, but now there's a 1/4 inside every one of these components. And now our losses will be equivalent. So when I run this, you see that the gradients are now identical. So long story short, with this simple example, when you step through it, you can see that basically the reason that this is not correct is because in the same way as here in the MSE loss, the loss that we're calculating here in the model is using a reduction of mean as well. So where's the loss? F dot cross entropy. And by default, the reduction here in cross entropy is also, I don't know why they don't show it, but it's the mean loss at all the B by T elements, right? So there's a reduction by mean in there, and if we're just doing this gradient accumulation here, we're missing that. And so the way to fix this is to simply compensate for the number of gradient accumulation steps, and we can in the same way divide this loss. So in particular here, the number of steps that we're doing is loss equals loss divided gradient accumulation steps. So even Copilot gets the modification. But in the same way exactly, we are scaling down the loss so that when we do loss dot backward, which basically corresponds to a sum in the objective, we are summing up the already normalized loss. And therefore, when we sum up the losses divided by grad accum steps, we are recovering the additional normalizer. And so now these two will be, now this will be equivalent to the original sort of optimization, because the gradient will come out the same. Okay, so I had to do a few more touch-ups, and I launched the optimization here. So in particular, one thing we want to do, because we want to print things nicely, is, well, first of all, we need to create like an accumulator over the loss. We can't just print the loss because we'd be printing only the final loss at the final micro step. So instead we have a loss accum, which I initialize at 0, and then I accumulate the loss into it. And I'm using detach so that I'm detaching the tensor from the graph, and I'm just trying to keep track of the values. So I'm making these leaf nodes when I add them. So that's loss accum, and then we're printing that here instead of loss. And then in addition to that, I had to account for the grad accum steps inside the tokens processed, because now the tokens processed per step is b times t times gradient accumulation. So long story short, here we have the optimization. It looks reasonable, right? We're starting at a good spot. We calculated the grad accum steps to be 32, and we're getting about 3 seconds here, right? And so this looks pretty good. Now, if you'd like to verify that your optimization and the implementation here is correct and you're working on the side, well, now because we have the total batch size and the gradient accumulation steps, our setting of B is purely a performance optimization kind of setting. So if you have a big GPU, you can actually increase this to 32 and you'll probably go a bit faster. If you have a very small GPU, you can try 8 or 4. But in any case, you should be getting the exact same optimization and the same answers up to like a floating point error, because the gradient accumulation kicks in and can handle everything serially as necessary. So that's it for gradient accumulation, I think. Okay, so now is the time to bring out the heavy weapons. You've noticed that so far we've only been using a single GPU for training, but actually I am paying for 8 GPUs here, and so we should be putting all of them to work. And in particular, they're all going to collaborate and optimize over tokens at the same time and communicate so that they're all kind of collaborating on the optimization. For this, we are going to be using the distributed data parallel from PyTorch. There's also a legacy data parallel, which I recommend you not use, and that's kind of like, legacy. Distributed data parallel works in a very simple way. We have 8 GPUs, so we're going to launch 8 processes, and each process is going to be assigned a GPU. And for each process, the training loop and everything we've worked on so far is going to look pretty much the same. Each GPU, as far as it's concerned, is just working on exactly what we've built so far. But now secretly, there's 8 of them, and they're all going to be processing slightly different parts of the data. And we're going to add one more part where once they all calculate their gradients, there's one more part where we do an average of those gradients. And so that's how they're going to be collaborating on the computational workload here. So to use all 8 of them, we're not going to be launching our script anymore with just PyTorch train gpt2.py. We're going to be running it with a special command called torchrun in PyTorch. We'll see that in a bit. And torchrun, when it runs our Python script, will actually make sure to run 8 of them in parallel. And it creates these environmental variables where each of these processes can look up which one of the processes it is. So for example, torchrun will set rank, local rank, and world size environmental variables. And so this is a bad way to detect whether DDP is running. So if we're using torchrun, if DDP is running, then we have to make sure that CUDA is available, because I don't know that you can run this on CPU anymore, or that makes sense to do. This is some setup code here. The important part is that there's a world size, which for us will be 8. That's the total number of processes running. There's a rank, which is each process will basically run the exact same code at the exact same time roughly, but the only difference between these processes is that they all have a different DTP rank. So the GPU 0 will have DTP rank of 0, GPU 1 will have rank of 1, etc. So otherwise they're all running the exact same script. It's just that DDP rank will be a slightly different integer. And that is the way for us to coordinate that they don't, for example, run on the same data. We want them to run on different parts of the data and so on. Now, local rank is something that is only used in a multi-node setting. We only have a single node with 8 GPUs. And so local rank is the rank of the GPU on a single node. So from 0 to 7 as an example. But for us, we're mostly going to be running on a single box. So the things we care about are rank and world size. This is 8, and this will be whatever it is depending on the GPU that this particular instantiation of the script runs on. Now here we make sure that according to the local rank, we are setting the device to be CUDA colon, and colon indicates which GPU to use if there are more than one GPUs. So depending on the local rank of this process, it's going to use just the appropriate GPU. So there's no collisions on which GPU is being used by which process. And finally, there's a Boolean variable that I like to create, which is the DDP rank equals 0. So the master process is arbitrarily process number 0, and it does a lot of the printing, logging, checkpointing, etc. And the other processes are thought of mostly as compute processes that are assisting. And so master process 0 will have some additional work to do. All the other processes will mostly just be doing forward backwards. And if we're not using DDP and none of these variables are set, we revert back to single GPU training. So that means that we only have rank 0, the world size is just 1, and we are the master process, and we try to auto-detect the device, and this is world as normal. So far all we've done is we've initialized DDP, and in the case where we're running with torch run, which we'll see in a bit, there's going to be 8 copies running in parallel. Each one of them will have a different rank. And now we have to make sure that everything happens correctly afterwards. So the tricky thing with running multiple processes is you always have to imagine that there's going to be 8 processes running in parallel. So as you read the code now, you have to imagine there's 8 Python interpreters running down these lines of code. And the only difference between them is that they have a different DDP rank. So they all come here, they all pick the exact same seed. They all make all of these calculations, completely unaware of the other copies running, roughly speaking, right? So they all make the exact same calculations, and now we have to adjust these calculations to take into account that there's actually like a certain world size and certain ranks. So in particular, these micro batches and sequence lengths, these are all just per GPU, right? So now there's going to be num processes of them running in parallel. So we have to adjust this, right? Because the Graticum steps now is going to be total batch size divided b times t times DDP world size, because each process will do b times t, and there's this many of them. And so in addition to that, we want to make sure that this fits nicely into total batch size, which for us it will, because 16 times 124 times 8 GPUs is 131 K, and so 524,288. This means that our Graticum will be 4 with the current settings, right? So there's going to be 16 times 124 processed in each GPU, and then there's 8 GPUs, so we're going to be doing 131,000 tokens in a single forward-backward on the 8 GPUs. So we want to make sure that this fits nicely so that we can derive a nice gradient accumulation steps. And yeah, let's just adjust the comments here, times DDP world size. Okay, so each GPU calculates this. Now this is where we start to run into issues, right? So each process is going to come by a print, and they're all going to print. So we're going to have 8 copies of these prints. So one way to deal with this is exactly this master process variable that we have. So if master process, then guard this. And that's just so that we just print this a single time, because otherwise all the processes would have computed the exact same variables, and there's no need to print this 8 times. Before getting into the data loader, we're going to have to refactor it, obviously. Maybe at this point is we should do some prints and just take it out for a spin and exit at this point. So import sys and sys.exit and print I am GPU DDP rank. I am GPU DDP rank, and print by. So now let's try to run this and just see how this works. So let's take it for a spin just so we see what it looks like. So normally we used to launch Python train gpt2.py like this. Now we're going to run with torch run, and this is what it looks like. So torch run standalone, number of processes, for example, is 8 for us because we have 8 GPUs, and then train gpt2.py. So this is what the command would look like. And torch run, again, will run 8 of these. So let's just see what happens. So first, it gets a little busy, so there's a lot going on here. So First of all, there's some warnings from distributed, and I don't actually know that these mean anything. I think this is just like the code is setting up and the processes are coming online, and we're seeing some preliminary failure to collect while the processes come up. I'm not 100% sure about that. But we start to then get into actual prints. So all the processes went down, and then the first print actually comes from process 5, just by chance. And then it printed, so process 5 basically got here first. It said, I'm GPU 5 by, and then these prints come from the master process. So process 5 just finished first for whatever reason. It just depends on how the operating system scheduled the processes to run. Then GPU 0 ended, then GPU 3 and 2. And then probably process 5 or something like that has exited. And DDP really doesn't like that because we didn't properly dispose of the multi-GPU setting. And so process group has not been destroyed before we destruct. So it really doesn't like that. And in an actual application, we would want to call destroy process group so that we clean up DDP properly. And so it doesn't like that too much. And then the rest of the GPUs finish, and that's it. So basically, we can't guarantee when these processes are running. It's totally arbitrary, but they are running in parallel. We don't want them to be printing. And next up, let's erase this. Next up, we want to make sure that when we create data loader light, we need to now make it aware of this multi-process setting, because we don't want all the processes to be loading the exact same data. We want every process to get its own chunk of data so that they're all working on different parts of the data set, of course. So let's adjust that. So one particularly simple and a naive way to do this is we have to make sure that we pass in the rank and the size to the data loader. And then when we come up here, we see that we now take rank and processes and we save them. Now, the current position will not be 0 because what we want is we want to stride out all the processes. So one way to do this is we basically take self.b times self.t and then multiply it by the process rank. So process rank 0 will start at 0, but process rank 1 now starts at b times t. Process rank 2 starts at 2 times b times t, etc. So that is the initialization. Now they still do this identically, but now when we advance, we don't advance by b times t, we advance by b times t times number of processes, right? So basically, the total number of tokens that we're consuming is b times t times num processes, and they all go off to a different rank, and the position has to advance by the entire chunk. And then here b times t times self.num processes plus 1 would be to exceed number of tokens, and then we're going to loop. And when we loop, we want to, of course, loop in the exact same way. So we sort of like reset back. So this is the simplest change that I can find for kind of a very simple distributed data loader light. And you can notice that if process rank is 0 and num processes is 1, then the whole thing will be identical to what we had before. But now we can have actually multiple processes running, and this should work fine. So that's the data loader. Okay, so next up, once they've all initialized the data loader, they come here and they all create a GPT model. So we create 8 GPT models on 8 processes, but because the seeds are fixed here, they all create the same identical model. They all move it to the device of their rank, and they all compile the model. And because the models are identical, there are 8 identical compilations happening in parallel, but that's okay. Now, none of this changes because that is on a per step basis, and we're currently working kind of within step because we need to all the changes we're making are kind of like a within step changes. Now, the important thing here is when we construct the EMP model, we actually have a bit of work to do here. Get logits is deprecated, so create model. We need to actually wrap the model into the distributed data parallel container. So this is how we wrap the model into the DDP container. And these are the docs for DDP, and they're quite extensive. And there's a lot of caveats and a lot of things to be careful with because everything complexifies times 10 when multiple processes are involved. But roughly speaking, this device IDs, I believe, has to be passed in. Now, unfortunately, the docs for what device IDs is extremely unclear. So when you actually like come here, this comment for what device IDs is roughly nonsensical, but I'm pretty sure it's supposed to be the DDP local rank. So not the DDP rank, the local rank. So this is what you pass in here. This wraps the model. And in particular, what DDP does for you is in a forward pass, it actually behaves identically. So my understanding of it is nothing should be changed in the forward pass. But in the backward pass, as you are doing the backward pass, in the simplest setting, once the backward pass is over on each independent GPU has the gradient for all the parameters. And what DDP does for you is once the backward pass is over, it will call what's called all reduce. And it basically does an average across all the ranks of their gradients. And then it will deposit that average on every single rank. So every single rank will end up with the average on it. And so basically that's the communication. It just synchronizes and averages the gradients. And that's what DDP offers you. Now DDP actually is a little bit more involved than that, because as you are doing the backward pass through the layers of the transformer, it actually can dispatch communications for the gradient while the backward pass is still happening. So there's overlap of the communication of the gradients and the synchronization of them and the backward pass. And this is just more efficient and to do it that way. So that's what DDP does for you. Forward is unchanged and backward is mostly unchanged, and we're tacking on this average, as we'll see in a bit. Okay, so now let's go to the optimization. Nothing here changes. Let's go to the optimization here, the inner loop, and think through the synchronization of these gradients in the DDP. So basically by default, what happens, as I mentioned, is when you do loss.backward here, it will do the backward pass and then it will synchronize the gradients. The problem here is because of the gradient accumulation steps loop here, we don't actually want to do the synchronization after every single loss.backward, because we are just depositing gradients and we're doing that serially and we just want them adding up, and we don't want to synchronize every single time. That would be extremely wasteful. So basically we want to add them up, and then on the very last, it's only on the very last step when microstep becomes grad steps -1, only at that last step do we want to actually do the all reduce to average up the gradients. So to do that, we come here, and the official sanctioned way, by the way, is to do this no sync context manager. So PyTorch says this is a context manager to disable gradient synchronization across DDP processes. So within this context, gradients will be accumulated, and basically when you do no sync, there will be no communication. So they are telling us to do with DDP no sync, do the gradient accumulate grads, and then they are asking us to do DDP again with another input and dot backward. And I just really don't love this. I just really don't like it. The fact that you have to copy paste your code here and use a context manager, and this is just super ugly. So when I went to the source code here, you can see that when you enter, you simply toggle this variable, this require backward grad sync. And this is being toggled around and changed. And this is the variable that basically, if you step through it, is being toggled to determine if the gradient is going to be synchronized. So I actually just kind of like to use that directly. So instead, what I like to do is the following. Right here before the loss.backward, if we are using DDP, then basically we only want to synchronize. We only want this variable to be true when it is the final iteration. In all the other iterations inside the microsteps, we want it to be false. So I just toggle it like this. So require backward grad sync should only turn on when the microstep is the last step. And so I'm toggling this variable directly, and I hope that that impacts loss.backward. And this is a naughty thing to do because, you know, they could probably change the DDP and this variable will go away. But for now, I believe this works and it allows me to avoid the use of context managers and code duplication. I'm just toggling the variable, and then loss.backward will not synchronize most of the steps, and it will synchronize the very last step. And so once this is over and we come out, every single rank will suddenly magically have the average of all the gradients that were stored on all the ranks. So now we have to think through whether that is what we want, and also if this suffices, and how it works with the loss and what is loss accum. So let's think through that now. And the problem I'm getting at is that we've averaged the gradients, which is great, but the loss accum has not been impacted yet, and this is outside of the DDP container, so that is not being averaged. And so here, when we are printing loss accum, well, presumably we're only going to be printing on the master process, rank 0, and it's just going to be printing the losses that it saw on its process. But instead, we want it to print the loss over all the processes and the average of that loss, because we did average of gradients, so we want the average of loss as well. So simply here after this, this is the code that I've used in the past. And instead of lossf, we want loss accum. So if DDP, again, then dist is a PyTorch distributed. I import it, where do I import it? Oh gosh. So this file is starting to get out of control, huh? So so import torch.distributed as dist. So dist.allreduce, and we're doing the average on loss accum. And so this loss accum tensor exists on all the ranks. When we call allreduce of average, it creates the average of those numbers, and it deposits that average on all the ranks. So all the ranks after this call will now contain loss accum averaged up. And so when we print here on the master process, the loss accum is identical in all the other ranks as well. So here, if master process, oops, we want to print like this. Okay, and finally, we have to be careful because we're now processing even more tokens. So times DDP world size, that's the number of tokens that we've processed up above. And everything else should be fine. The only other thing to be careful with is, as I mentioned, you want to destroy the process group so that we are nice to nickel and it's not going to DDP, and it's not going to complain to us when we exit here. So that should be it. Let's try to take it for a spin. Okay, so I launched the script and it should be printing here imminently. We're now training with 8 GPUs at the same time. So the gradient accumulation steps is not 32, it is now divide 8, and it's just 4. Otherwise, this is what the optimization now looks like. And wow, we're going really fast. So we're processing 1.5 million tokens per second now. So these are some serious numbers. And the tiny Shakespeare dataset is so tiny that we're just doing like so many epochs over it, most likely. But this is roughly what it looks like. One thing that I had to fix, by the way, is that this was model.configure optimizers, which now doesn't work because model now is a DDP model. So instead, this has to become raw model.configure optimizers, where raw model is something I create here. So right after I wrap the model into DDP, I have to create the raw model, which in the case of DDP is a model.module, is where it stores the raw NN module of GPT-2 as we have it, which contains the configure optimizers function that we want to call. So that's one thing that I have to fix. Otherwise, this seems to run. Now, one thing you'll notice is that when you actually compare this run and the numbers in it to the just running a single GPU, you'll notice that this is a single GPU run with 32 grad accum. The numbers won't exactly match up. And that's kind of a boring reason for why that happens. The reason for that is that in the data loader, we're basically just iterating through batches in a slightly different way, because now we're looking for an entire page of data. And if that page for all the GPUs, if that chunk exceeds the number of tokens, we just loop. And so actually the single GPU and the 8 GPU process will end up resetting in a slightly different manner. And so our batches are slightly different. And so we get slightly different numbers. But one way to convince yourself that this is okay is just make the total batch size much smaller and the B and a T. And then, so I think I used 4 times 124 times 8. So I used 32,768 as the total batch size. And then, so I made sure that a single GPU will do 8 gradient accumulation steps, and then I did multi-GPU. And then you're reducing the boundary effects of the data loader, and you'll see that the numbers match up. So long story short, we're now going really, really fast. The optimization is mostly consistent with GPT-2 and 3 hyperparameters. And we have outgrown our tiny Shakespeare file. and we want to upgrade it. So let's move to that next. So let's now take a look at what datasets were used by GPT-2 and GPT-3. So GPT-2 used this web text dataset that was never released. There's an attempt at reproducing it called Open Web Text. So basically, roughly speaking, what they say here in the paper is that they scraped all outbound links from Reddit, and then with at least 3 karma, and that was kind of like their starting point, and they collected all the web pages and all the text in them. And so this was 45 million links, and this ended up being 40 gigabytes of text. So so that's roughly what GPT-2 says about its dataset. So it's basically outbound links from Reddit. Now, when we go over to GPT-3, there's a training dataset section, and that's where they start to talk about Common Crawl, which is a lot more used. Actually, I think even GPT-2 talked about Common Crawl. But basically, it's not a very high quality dataset all by itself because it is extremely noisy. This is a completely random subset of the internet, and it's much worse than you think. So people go into great lengths to filter Common Crawl because there's good stuff in it, but most of it is just like ad spam, random tables and numbers and stock tickers, and it's just total mess. So that's why people like to train on these data mixtures that they curate and are careful with. So a large chunk of these data mixtures typically will be Common Crawl, like for example 50% of the tokens will be Common Crawl. But then here in GPT-3, they're also using web text 2 from before, so that's Reddit outbound. But they're also adding, for example, books, and they're adding Wikipedia. There's many other things you can decide to add. Now, this dataset for GPT-3 was also never released. So today, some of the datasets that I'm familiar with that are quite good and would be representative of something along these lines are number one, the Red Pajama dataset, or more specifically, for example, the Slim Pajama subset of the Red Pajama dataset, which is a cleaned and deduplicated version of it. And just to give you a sense, again, it's a bunch of Common Crawl, C4, which is also, as far as I know, more Common Crawl, but processed differently. And then we have GitHub, Books, Archive, Wikipedia, Stack Exchange. These are the kinds of datasets that would go into these data mixtures. Now, specifically the one that I like that came out recently is called FineWeb dataset. So this is an attempt to basically collect really high quality Common Crawl data and filter it, in this case, to 15 trillion tokens. And then in addition to that, more recently, Hugging Face released this FineWeb EDU subset, which is 1.3 trillion of educational and 5.4 trillion of high educational content. So basically, they're trying to filter Common Crawl to very high quality educational subsets. And this is the one that we will use. There's a long web page here on FineWeb, and they go into a ton of detail about how they process the data, which is really fascinating reading, by the way. And I would definitely recommend, if you're interested into data mixtures and so on, and how data gets processed at these scales, look at this page. And more specifically, we'll be working with the FineWeb EDU, I think. And it's basically educational content from the internet. They show that training on educational content in their metrics works really, really well. And we're going to use this sample 10 billion tokens subsample of it, because we're not going to be training on trillions of tokens. We're just going to train on 10 billion sample of the FineWeb EDU, because empirically in my previous few experiments, this actually suffices to really get close to GPT-2 performance. And it's simple enough to work with. And so let's work with the sample 10 BT. So our goal will be to download it, process it, and make sure that our data loader can work with it. So let's get to that. Okay, so I introduced another file here that will basically download FineWeb EDU from Hugging Face datasets. It will pre-process and pre-tokenize all of the data, and it will save data shards to a folder on local disk. And so while this is running, just wanted to briefly mention that you can kind of look through the dataset viewer here just to get a sense of what's in here. And it's kind of interesting. I mean, it basically looks like it's working fairly well. Like it's talking about nuclear energy in France. It's talking about Mexican America, some Mac.PyJs, etc. So actually it seems like their filters are working pretty well. The filters here, by the way, were applied automatically using Llama 370B, I believe. And so basically LLMs are judging which content is educational, and that ends up making it through the filter. So that's pretty cool. Now, in terms of the script itself, I'm not going to go through the full script because it's not as interesting and not as LLM centric. But when you run this, basically, number one, we're going to load the dataset, which this is all Hugging Face code running this. You're going to need to pip install datasets. So it's downloading the dataset, then it is tokenizing all of the documents inside this dataset. Now, when we tokenize the documents, you'll notice that to tokenize a single document, we first start the tokens with the end of text token. And this is a special token in the GPT-2 tokenizer, as you know. So 50,256 is the ID of the end of text. And this is what begins a document, even though it's called end of text. But this is the first token that begins a document. Then we extend with all of the tokens of that document. Then we create a NumPy array out of that. We make sure that all the tokens are between, okay, let me debug this. Okay, so apologies for that. It just had to do with me using a float division in Python. It must be integer division so that this is an int and everything is nice. Okay, but basically the tokenization here is relatively straightforward. Returns tokens in mp.un16. We're using un.16 to save a little bit of space because 2 to the 16 minus 1 is 65,000. So the GPT-2 max token ID is well below that. And then here, there's a bunch of multiprocessing code, and it's honestly not that exciting, so I'm not gonna step through it, but we're loading the dataset, we're tokenizing it, and we're saving everything to shards. And the shards are NumPy files. So just storing a NumPy array, and which is very, very similar to torch tensors. And the first shard, 000, is a validation shard, and all the other shards are training shards. And as I mentioned, they all have 100 million tokens in them exactly. And that just makes it easier to work with, to shard the files, because if we just have a single massive file, sometimes they can be hard to work with on the disk. And so sharding it is just kind of nicer from that perspective. And yeah, so we'll just let this run. This will be probably 30-ish minutes or so, and then we're going to come back to actually train on this data. And we're going to be actually doing some legit pre-training in this case. This is a good data set. We're doing lots of tokens per second. We have 8 GPUs. The code is ready. And so we're actually going to be doing a serious training run. So let's get back in a bit. Okay, so we're back. So if we ls edu find web, we see that there's now 100 shards in it. And that makes sense because each shard is 100 million tokens. So 100 shards of that is 10 billion tokens in total. Now swinging over to the main file, I made some adjustments to our data loader again, and that's because we're not running with Shakespeare anymore. We want to use the find web shards. And so you'll see some code here that additionally basically can load these shards. We load the UN16 NumPy file. We convert it to a torch.long tensor, which is what a lot of the layers up top expect by default. And then here we're just enumerating all the shards. I also added a split to data loader light, so we can load the split train, but also the split val, the 0 split. And then we can load the shards, and then here we also have not just the current position now, but also the current shard. So we have a position inside a shard, and then when we run out of tokens in a single shard, we first advance the shard and loop if we need to, and then we get the tokens and readjust the position. So this data loader will now iterate all the shards as well. So I changed that, and then the other thing that I did while the data was processing is our train loader now has split train, of course. And down here I set up some numbers. So we are doing 2 to the 19 tokens per step, and we want to do roughly 10 billion tokens. Because that's how many unique tokens we have. So if we did 10 billion tokens, then divide that by 2 to the 19, we see that this is 19,073 steps. So that's where that's from. And then the GPT-3 paper says that they warm up the learning rate over 375 million tokens. So I came here and 375 E6 tokens, divide 2 to the 19 is 715 steps. So that's why warm-up steps is set to 715. So this will exactly match the warm-up schedule that GPT-3 used. And I think 715, by the way, is very mild, and this could be made significantly more aggressive. Probably even like 100 is good enough. But it's okay, let's leave it for now. so that we have the exact hyperparameters of GPT-3. So I fixed that, and then that's pretty much it. We can run. So we have our script here, and we can launch. And actually, sorry, let me do one more thing. Excuse me. For my GPU, I can actually fit more batch size, and I believe I can fit 64 on my GPU as a micro batch size. So let me try that. I could be misremembering, but that means 64 times 124 per GPU, and then we have 8 GPUs. So that means we would not even be doing gradient accumulation if this fits, because this just multiplies out to the full total batch size. So no gradient accumulation, and that would run pretty quickly if that fits. Let's go. I mean, if this works, then this is basically a serious pre-training run. We're not logging, we're not evaluating the validation split, we're not running any evaluations yet. So we haven't crossed our T's and dotted our I's, but if we let this run for a while, we're going to actually get a pretty good model, and the model that might even be on par with or better than GPT-2 124M. Okay, so it looks like everything is going great. We're processing 1.5 million tokens per second. Everything here looks good. We're doing 330 milliseconds per iteration, and we have to do a total of, where are we printing that? 1973. So 19073 times 0.33 is this many seconds, this many minutes. So this will run for 1.7 hours. So 1.5 hour run like this. And we don't even have to use gradient accumulation, which is nice. And you might not have that luxury in your GPU. In that case, just start decreasing the batch size until things fit, but keep it to nice numbers. So that's pretty exciting. We're currently warming up the learning rate, so you see that it's still very low, 1e -4. So this will ramp up over the next few steps all the way to 6e -4 here. Very cool. So now what I'd like to do is let's cross the T's and dot our I's. Let's evaluate on the validation split, and let's try to figure out how we can run evals, how we can do logging, how we can visualize our losses, and all the good stuff. So let's get to that before we actually do the run. Okay, so I've adjusted the code so that we're evaluating on the validation split. So creating the val loader just by passing in split equals val, that will basically create a data loader just for the validation shard. The other thing I did is in the data loader, I introduced a new function reset, which is called at init, and it basically resets the data loader. And that is very useful because when we come to the main training loop now, so this is the code I have added, and basically every 100th iteration, including the 0th iteration, we put the model into evaluation mode, we reset the val loader, and then no gradients involved. We're going to basically accumulate the gradients over, say, 20 steps, and then average it all up and print out the validation loss. And so that basically is the exact same logic as the training loop, roughly, but there's no loss that backward. It's only inference. We're just measuring the loss. We're adding it up. Everything else otherwise applies and is exactly as we've seen it before. And so this will print the validation loss every 100th iteration, including on the very first iteration. So that's nice. That will tell us a little bit about how much we're overfitting. That said, we have roughly infinity data, so we're mostly expecting our train and val loss to be about the same. But the other reason I'm kind of interested in this is because we can take the GPT-2 124M as OpenAI released it, we can initialize from it, and we can basically see what kind of loss it achieves on the validation loss as well. And that gives us kind of an indication as to how much that model would generalize to 124M. But it's not, to FineWeb EDU validation split. That said, it's not a super fair comparison to GPT-2 because it was trained on a very different data distribution, but it's still kind of like an interesting data point. And in any case, you would always want to have a validation split in a training run like this so that you can make sure that you are not overfitting. And this is especially a concern if we were to make more epochs in our training data. So for example, right now we're just doing a single epoch, but if we get to a point where we want to train on 10 epochs or something like that, we would be really careful with maybe we are memorizing that data too much if we have a big enough model, and our validation split would be one way to tell whether that is happening. Okay, and in addition to that, if you remember, at the bottom of our script, we had all of this orphaned code for sampling from way back when. So I deleted that code and I moved it up to here. So once in a while, we sample a validation. Once in a while, we generate samples. And then we do that only every 100 steps, and we train on every single step. So that's how I have it structured right now, and I've been running this for 1,000 iterations. So here are some samples on iteration 1,000. Hello, I'm a language model, and I'm not able to get more creative. I'm a language model, and the languages file you're learning about here is the beginning of a computer. Okay, so this is all like pretty, this is still a garble, but we're only at iteration 1000, and we've only just barely reached the maximum learning rate. So this is still learning. We're about to get some more samples coming up in 1100. Okay. Okay, this is, the model is still a young baby. Okay, so basically all of this sampling code that I've put here, everything should be familiar to you and came from before. The only thing that I did is I created a generator object in PyTorch so that I have a direct control over the sampling of the random numbers, because I don't want to impact the RNG state of the random number generator that is the global one used for training. I want this to be completely outside of the training loop. And so I'm using a special sampling RNG, and then I make sure to seed it, that every single rank has a different seed. And then I pass in here where we sort of consume random numbers in multinomial, where the sampling happens. I make sure to pass in the generator object there. Otherwise, this is identical. Now, the other thing is you'll notice that we're running a bit slower. That's because I actually had to disable torch.compile to get this to sample. And so we're running a bit slower. So for some reason it works with no torch compile, but when I torch compile my model, I get a really scary error from PyTorch, and I have no idea how to resolve it right now. So probably by the time you see this code released or something like that, maybe it's fixed. But for now, I'm just going to do end false, and I'm going to bring back torch compile, and you're not going to get samples. And I think I'll fix this later. By the way, I will be releasing all this code. And actually, I've been very careful about making git commits every time we add something. And so I'm going to release the entire repo that starts completely from scratch all the way to now and after this as well. And so everything should be exactly documented in the git commit history. And so I think that will be nice. So hopefully by the time you go to GitHub, this is removed and it's working, and I will have fixed the bug. Okay, so I have the optimization running here, and it's stepping, and we're on step 6,000 or so we're about 30% through training. Now, while this is training, I would like to introduce one evaluation that we're going to use to supplement the validation set, and that is the HelloSwag eval. So HelloSwag comes from this paper back in 2019, so it's a 5-year-old eval now. And the way HelloSwag works is that it's basically a sentence completion dataset. So it's a multiple choice. For every one of these questions, we have basically a shared context, like a woman is outside with a bucket and a dog. The dog is running around trying to avoid bath. She, A, rinses the bucket off with soap and blow dry the dog's head. B, uses a hose to keep it from getting soapy. C, gets the dog wet and it runs away again. Or D, gets into a bathtub with the dog. And so basically the idea is that these multiple choice are constructed so that one of them is a natural continuation of the sentence and the others are not. And the others might not make sense, like uses the hose to keep it from getting soapy. That makes no sense. And so what happens is that models that are not trained very well are not able to tell these apart, but models that have a lot of world knowledge and can tell and can tell a lot about the world will be able to create these completions. And these sentences are sourced from ActivityNet and from WikiHow. And at the bottom of the paper, there's kind of like a cool chart of the kinds of domains in WikiHow. So there's a lot of sentences from computers and electronics and homes and garden, and it has kind of a broad coverage of the kinds of things you need to know about the world in order to find the most likely completion and the identity of that completion. One more thing that's kind of interesting about HelloSwag is the way it was constructed is that the incorrect options are deliberately adversarially sourced. So they're not just random sentences, they're actually sentences generated by language models. And they're generated in such a way that language models basically find them difficult, but humans find them easy. And so they mentioned that humans have a 95% accuracy on this set, but at the time, the state-of-the-art language models had only 48%. And so at the time, this was a good benchmark. Now, you can read the details of this paper to learn more. The thing to point out, though, is that this is 5 years ago. And since then, what happened to HelloSwag is that it's been totally just solved. And so now the language models here are 96%. So basically the 4%, the last 4% is probably errors in the data set, or the questions are really, really hard. And so basically this data set is kind of crushed with respect to language models. But back then, the best language model was only at about 50%. This is how far things got. But still, the reason people like HelloSwag, and it's not used, by the way, in GPT-2, but in GPT-3, there is HelloSwag eval. And lots of people use HelloSwag. And so for GPT-3, we have results here that are cited. So we know what percent accuracies GPT-3 attains at all these different model checkpoints for HelloSwag eval. And the reason people like it is because HelloSwag is a smooth eval, and it is an eval that offers quote unquote early signal. So early signal means that even small language models are going to start at the random chance of 25%, but they're going to slowly improve, and you're going to see 25, 26, 27, etc. And you can see slow improvement even when the models are very small and it's very early. So it's smooth, it has early signal, and it's been around for a long time. So that's why people kind of like this eval. Now, the way that we're going to evaluate this is as follows. As I mentioned, we have a shared context, and this is kind of like a multiple choice task. But instead of giving the model a multiple choice question and asking it for A, B, C, or D, we can't do that because these models, when they are so small as we are seeing here, the models can't actually do multiple choice. They don't understand the concept of associating a label to one of the options of multiple choice. They don't understand that. So we have to give it to them in a native form. And the native form is a token completion. So here's what we do. We construct a batch of 4 rows and T tokens, whatever that T happens to be. Then the shared context, that is basically the context for the 4 choices, the tokens of that are shared across all of the rows. And then we have the 4 options. So we kind of like lay them out, and then only one of the options is correct. In this case, label 3, option 3. And so this is the correct option, and option 1, 2, and 4 are incorrect. Now, these options might be of different lengths. So what we do is we sort of like take the longest length, and that's the size of the batch, B by T. And then some of these here are going to be padded dimensions. So they're going to be unused. And so we need the tokens, we need the correct label, and we need a mask that tells us which tokens are active. And the mask is then 0 for these padded areas. So that's how we construct these batches. And then in order to get the language model to predict A, B, C, or D, the way this works is basically we're just going to look at the tokens, their probabilities, and we're going to pick the option that gets the lowest or the highest average probability for the token. So for the tokens, because that is the most likely completion according to the language model. So we're just going to look at the probabilities here and average them up across the options and pick the one with the highest probability, roughly speaking. So this is how we're going to do HelloSwag. And this is, I believe, also how GPT-3 did it. This is how GPT-3 did it, as far as I know. But you should note that some of the other evals where you might see HelloSwag may not do it this way. They may do it in a multiple choice format where you sort of give the context a single time and then the 4 completions. And so the model is able to see all the 4 options before it picks the best possible option. And that's actually an easier task for a model because you get to see the other options when you're picking your choice. But unfortunately, models at our size can't do that. Only models at a bigger size are able to do that. And so our models are actually slightly handicapped in this way that they are not going to see the other options. They're only going to see one option at a time, and they just have to assign probabilities, and the correct option has to win out in this metric. All right, so let's now implement this very briefly and incorporate it into our script. Okay, so what I've done here is I've introduced a new file called helloswag.py that you can take a look into. And I'm not going to step through all of it because this is not exactly like deep code. It's kind of like a little bit tedious, honestly, because what's happening is I'm downloading helloswag from GitHub and I'm rendering all of its examples, and there are a total of 10,000 examples. I am rendering them into this format. And so here at the end of this render example function, you can see that I'm returning the tokens of this 4 by t array of tokens, the mask, which tells us which parts are the options and everything else is 0, and the label, that is the correct label. And so that allows us to then iterate the examples and render them. And I have an evaluate function here, which can load a gpt2 from Hugging Face, and it runs the eval here. And it basically just calculates, just as I described, it predicts the option that has the lowest or the highest probability. And the way to do that actually is we can basically evaluate the cross entropy loss. So we're basically evaluating the loss of predicting the next token in a sequence. And then we're looking at the row that has the lowest average loss. And that's the option that we pick as the prediction. And then we do some stats and prints and stuff like that. So that is a way to evaluate helloswag. Now, if you go up here, I'm showing that for GPT-2 124M, if you run this script, you're going to see that helloswag gets 29.55%. So that's the performance we get here. Now remember that random chance is 25%, so we haven't gone too far. And GPT-2 XL, which is the biggest, the GPT-2, gets all the way up to 49% roughly. So these are pretty low values considering that today's state of the art is more like 95%. So these are definitely older models by now. And then there's one more thing called Eleuther harness, which is a very common piece of infrastructure for running evals for language models. And they get slightly different numbers. And I'm not 100% sure what the discrepancy is for these. It could be that they actually do the multiple choice instead of just the completions, and that could be the discrepancy. But I'm not 100% sure about that. I'd have to take a look. But for now, our script reports 29.55, and so that is the number that we'd like to beat if we are training a GPT-2 124M from scratch and ourselves. So now I'm going to go into actually incorporating this eval into our main training script, and basically because we want to evaluate it in a periodic manner so that we can track helloswag and how it evolves over time, and see when and if we cross this 29.55 sort of region. So let's now walk through some of the changes to train gpt2.py. The first thing I did here is I actually made use compile optional kind of, and I disabled it by default. And the problem with that is, the problem with compile is that unfortunately it does make our code faster, but it actually breaks the evaluation code and the sampling code. It gives me a very gnarly message and I don't know why. So hopefully by the time you get to the code base when I put it up on GitHub, we're gonna fix that by then. But for now I'm running without torch compile, which is why you see this be a bit slower. So we're running without torch compile. I also created a log directory, log, where we can place our log.txt, which will record the train loss, validation loss, and the helloswag accuracies. So a very simple text file, and we're gonna open for writing so that it sort of starts empty, and then we're gonna append to it. I created a simple variable that helps tell us when we have a last step. And then basically periodically inside this loop, every 250th iteration or at the last step, we're gonna evaluate the validation loss. And then every 250th iteration, we are gonna evaluate helloswag, but only if we are not using compile, because compile breaks it. So I'm gonna come back to this code for evaluating helloswag in a second. And then every 250th iteration as well, we're also gonna sample from the model. And so you should recognize this as our ancient code from way back when we started the video, and we're just sampling from the model. And then finally here, these are, if we're not, after we validate, sample, and evaluate HelloSwag, we actually do a training step here. And so this is one step of training, and you should be pretty familiar with all of what this does. And at the end here, once we get our training loss, we write it to the file. So the only thing that changed that I really added is this entire section for HelloSwag eval. And the way this works is I'm trying to get all the GPUs to collaborate on the HelloSwag. And so we're iterating all the examples, and then each process only picks the examples that assign to it. So we sort of take I and mod it by the world size, and we have to make it equal to rank. Otherwise we continue. And then we render an example, put it on the GPU, we get the logits. Then I create a helper function that helps us basically predict the option with the lowest loss. So this comes here, the prediction. And then if it's correct, we sort of keep a count. And then if multiple processes were collaborating on all this, then we need to synchronize their stats. And so one way to do that is to package up our statistics here into tensors, which we can then call this.allReduceOn and sum. And then here we sort of unwrap them from tensors so that we just have ints. And then here the master process will print and log the HelloSwag accuracy. So that's kind of it. And that's what I'm running right here. So you see this optimization here. And we just had a generation. And this is step 10,000 out of about 20,000, right? So we are halfway done. And these are the kinds of samples that we are getting at this stage. So let's take a look. Hello, I'm a language model. So I'd like to use it to generate some kinds of output. Hello, I'm a language model, and I'm a developer for a lot of companies. Hello, I'm a language model. Let's see if I can find any fun one. I don't know, you can go through this yourself, but certainly the predictions are getting less and less random. It seems like the model is a little bit more self-aware and using language that is a bit more specific to it being a language model. Hello, I'm a language model, and like how the language is used to communicate, I'm a language model and are going to be speaking English and German. Okay, I don't know. So let's just wait until this optimization finishes, and we'll see what kind of samples we get. And we're also going to look at the train, val, and the HelloSwag accuracy and see how we're doing with respect to GPT-2. Okay, good morning. So focusing for a moment on the Jupyter notebook here on the right, I created a new cell that basically allows us to visualize the train, val, and hella, and the hella score. And you can step through this. It basically like parses the log file that we are writing. And a lot of this is just like boring matplotlib code, but basically this is what our optimization looks like. So we ran for 19,073 steps, which is roughly 10 billion tokens, which is, whoops, oh my gosh, which is one epoch of the sample 10B of FineWeb-EDU. On the left, we have the loss, and in the blue, we have the training loss. In orange, we have the validation loss. And in red, as a horizontal line, we have the OpenAI GPT-2 124M model checkpoint when it's just evaluated on the validation set of this FineWeb-EDU. So you can see that we are surpassing, this orange is below the red, so we're surpassing the validation set of this data set. And like I mentioned, the dataset distribution is very different from what GPT-2 trained on. So this is not an exactly fair comparison, but it's a good cross-check to look at. Now, we would ideally like something that is withheld and comparable and somewhat standard. And so for us, that is HelloSwag. And so on here, we see the HelloSwag progress we made from 25% all the way here. In red, we see the OpenAI GPT-2 124M model in red. So it achieves this HelloSwag here. And the GPT-3 model 124M, which was trained on 300 billion tokens, achieves green. So that's over here. So you see that we've basically surpassed the GPT-2 124M model right here, which is really nice. Now, interestingly, we were able to do so with only training on 10 billion tokens, while GPT-2 was trained on 100 billion tokens. So for some reason, we were able to get away with significantly fewer tokens for training. There are many possibilities as to why we could match or surpass this accuracy with only 10 billion training. So number one, it could be that OpenAI GPT-2 was trained on a much wider data distribution. So in particular, FineWeb EDU is all English, it's not multilingual, and there's not that much math in code. And so math and code and multilingual could have been stealing capacity from the original GPT-2 model, and basically that could be partially the reason why this is not working out. There's many other reasons. So for example, the HelloSwag eval is fairly old, maybe 5 years or so. It is possible that aspects of HelloSwag in some way, or even identically, have made it into the training set of FineWeb. We don't know for sure, but if that was the case, then we are basically looking at the training curve instead of the validation curve. So long story short, this is not a perfect eval, and there's some caveats here, but at least we have some confidence that we're not doing something completely wrong. And it's probably the case that when people try to create these data sets, they try to make sure that test sets that are very common are not part of the training set. For example, when Hugging Face created the FineWeb EDU, they use HelloSwag as an eval. So I would hope that they make sure that they deduplicate and that there's no HelloSwag in the training set, but we can't be sure. The other thing I wanted to address briefly is look at this loss curve. This looks really really wrong here. I don't actually know 100% what this is, and I suspect it's because the 10 billion sample of FineWeb EDU was not properly shuffled. And there's some issue here with the data that I don't fully understand yet, and there's some weird periodicity to it. And because we are in a very lazy way, sort of serializing all the tokens and just iterating on them from scratch without doing any permutations or any random sampling ourselves, I think we're inheriting some of the ordering that they have in the dataset. So this is not ideal. But hopefully by the time you get to this repo, some of these things, by the way, will hopefully be fixed. And I will release this build NanoGPT repo. And right now it looks a little ugly and preliminary. So hopefully by the time you get here, it's nicer. But down here, I'm going to show errata, and I'm going to talk about some of the things that happened after the video. And I expect that we will have fixed the small issue. But for now, basically, this shows that our training is not completely wrong. And it shows that we're able to surpass the accuracy with only 10x the token budget. And possibly it could be also that the dataset may have improved. So the original GPT-2 dataset was web text. It's possible that not a lot of care and attention went into the dataset. This was very early in LLMs, whereas now there's a lot more scrutiny on good practices around deduplication, filtering, quality filtering, and so on. And it's possible that the dataset we're training on is just of higher quality per token, and that could be giving us a boost as well. So a number of caveats to think about, but for now, we're pretty happy with this. Yeah. Now, the next thing I was interested in is, as you see, it's a morning now, so there was an overnight, and I wanted to basically see how far I could push the result. So to do an overnight run, I basically did, instead of 1 epoch, which took roughly 2 hours, I just did it times 4, so that would take 8 hours while I was sleeping. And so we did 4 epochs, or roughly 40 billion tokens of training. And I was trying to see how far we could get. And so this was the only change, and I reran the script. And when I point and read the log file at the 40B, this is what the curves look like. Okay, so to narrate this, number one, we are seeing this issue here with the periodicity through the different epochs and something really weird with the FineWeb EDU dataset, and that is to be determined. But otherwise, we are seeing that the HelloSwag actually went up by a lot, and we almost made it to the GPT-3 124M accuracy up here, but not quite. So it's too bad that I didn't sleep slightly longer. I think if this was a 5 epoch run, we may have gotten here. Now, one thing to point out is that if you're doing multi-epoch runs, we're not actually being very careful in our data loader, and we're not, this data loader goes through the data in exactly the same format and exactly the same order. And this is kind of suboptimal, and you would want to look into extensions where you actually permute the data randomly. You permute the documents around in every single shard on every single new epoch, and potentially even permute the shards. And that would go a long way into decreasing the periodicity, and it's also better for the optimization, so that you're not seeing things in the identical format, and you're introducing some randomness in how the documents follow each other. Because you have to remember that in every single row, these documents follow each other, and then there's the end of text token, and then the next document. So the documents are currently glued together in the exact same identical manner, but we actually want to break up the documents and shuffle them around, because the order of the documents shouldn't matter, and they shouldn't, basically we want to break up that dependence because it's a kind of a spurious correlation. And so our data loader is not currently doing that, and that's one improvement you could think of making. The other thing to point out is we're almost matching GPT-3 accuracy with only 40 billion tokens. GPT-3 trained on 300 billion tokens. So again, we're seeing about a 10x improvement here with respect to learning efficiency. The other thing I wanted to, and I don't actually know exactly what to attribute this to, other than some of the things that I already mentioned previously for the previous one. The other thing I wanted to briefly mention is the max LR here. I saw some people already play with this a little bit in a previous related repository. And it turns out that you can actually almost like 3x this. So it's possible that the maximum learning rate can be a lot higher. And for some reason, the GPT-3 hyperparameters that we are inheriting are actually extremely conservative, and you can actually get away with a higher learning rate and it would train faster. So a lot of these hyperparameters are quite tunable, and feel free to play with them, and they're probably not set precisely correctly. And it's possible that you can get away with doing this, basically. And if you wanted to exactly be faithful to GPT-3, you would also want to make the following difference. You'd want to come here, and the sequence length of GPT-3 is 2x. It's 2048 instead of 1024. So you would come here, change this to 2048 for T, and then if you want the exact same number of tokens, 500,000 per iteration or per step, you want to then decrease this to 32. So they still multiply to 500,000. So that would give your model sequence length equal to that of GPT-3. And in that case, basically the models would be roughly identical as far as I'm aware, because again, GPT-2 and GPT-3 are very, very similar models. Now we can also look at some of the samples here from the model that was trained overnight. So this is the optimization, and you see that here we stepped all the way to 76,290 also or so. And these are, the HelloSwag we achieved was 33.24. And these are some of the samples from the model. And you can see that if you read through this and pause the video briefly, you can see that they are a lot more coherent. And they're actually addressing the fact that it's a language model almost. So, hello, I'm a language model, and I try to be as accurate as possible. I'm a language model, not a programming language. I know how to communicate. I use Python. I don't know. If you pause this and look at it and then compare it to the model that was only trained for 10 billion, you will see that these are a lot more coherent, and you can play with this yourself. One more thing I added to the code, by the way, is this chunk of code here. So basically, right after we evaluate the validation loss, if we are the master process, in addition to logging the validation loss, every 5,000 steps, we're also going to save the checkpoint, which is really just the state dictionary of the model. And so checkpointing is nice just because you can save the model and later you can use it in some way. If you wanted to resume the optimization, then in addition to saving the model, we have to also save the optimizer state dict. Because remember that the optimizer has a few additional buffers because of Atom. So it's got the M and V, and you need to also resume the optimizer properly. You have to be careful with your RNG seeds, random number generators, and so on. So if you wanted to exactly be able to resume optimization, you have to think through the state of the training process. But if you just want to save the model, this is how you would do it. And one nice reason why you might want to do this is because you may want to evaluate the model a lot more carefully. So here we are only kind of like winging the HelloSwag eval, but you may want to use something nicer, like for example the Luther evaluation harness. So this is a way to also evaluate language models, and so it's possible that you may want to use basically different infrastructure to more thoroughly evaluate the models on different evaluations and compare it to the OpenAI GPT-2 model on many other tasks, like for example, that involve math, code, or different languages and so on. So this is a nice functionality to have as well. And then the other thing I wanted to mention is that everything we've built here, this is only the pre-training step. So the GPT here it dreams documents. It just predicts the next token. You can't talk to it like you can talk to ChatGPT. If you wanted to talk to the model, we have to fine-tune it into the chat format. And that's not actually like that complicated. If you're looking at supervised fine-tuning or SFT, really what that means is we're just swapping out a dataset into a dataset that is a lot more conversational, and there's a user assistant kind of structure, and we just fine-tune on it. And then we basically fill in the user tokens and we sample the assistant tokens. It's not a lot more deeper than that, but basically we swap out the dataset and continue training. But for now, we're going to stop at pre-training. One more thing that I wanted to briefly show you is that, of course, what we've built up today was building towards NanoGPT, which is this repository from earlier. But also there's actually another NanoGPT implementation, and it's hiding in a more recent project that I've been working on called LLM.C. And LLM.C is a pure C-CUDA implementation of GPT-2 or GPT-3 training, and it just directly uses CUDA and is written as C-CUDA. Now the NanoGPT here acts as reference code in PyTorch to the C implementation. So we're trying to exactly match up the two, but we're hoping that the C-CUDA is faster. And of course, currently that seems to be the case because it is a direct optimized implementation. So traingpt2.py in LLM.c is basically the NanoGPT. And when you scroll through this file, you'll find a lot of things that very much look like things that we've built up in this lecture. And then when you look at traingpt2.cu, this is the C-CUDA implementation. So there's a lot of MPI, Nickel, GPU, CUDA, C, C++, and you have to be familiar with that. But when this is built up, we can actually run the two side by side, and they're going to produce the exact same results, but LM.c actually runs faster. So let's see that. So on the left, I have PyTorch, NanoGPT looking thing. On the right, I have the LLMC call, and here I'm gonna launch the two. Both of these are going to be running on a single GPU, and here I'm putting the LM.c on GPU 1, and this one will grab GPU 0 by default. And then we can see here that LM.c compiled and then allocate space, and it's stepping. So basically, meanwhile, PyTorch is still compiling because Torch compile is a bit slower here than the LM.c NVCC C-CUDA compile. And so this program has already started running, and we're still waiting here for Torch compile. Now, of course, this is a very specific implementation to GPT-2 and 3. PyTorch is a very general neural network framework, so they're not exactly comparable. But if you're only interested in training GPT-2 and 3, LM.c is very fast. It takes less space, it's faster to start, and it's faster per step. And so PyTorch started stepping here. And as you can see, we're running at about 223,000 tokens per second here and about 185,000 tokens per second here. So quite a bit slower, but I don't have full confidence that I exactly squeezed out all the juice from the PyTorch implementation. But the important thing here is notice that if I align up the steps, you will see that the losses and the norms that are printed between these two are identical. So on the left, we have the PyTorch, and on the right, this C-CUDA implementation, and they're the same, except this one runs faster. So that's kind of, I wanted to show you also briefly LM.c, and this is a parallel implementation, and it's also something that you may want to play with or look at, and it's kind of interesting. Okay, so at this point, I should probably start wrapping up the video because I think it's getting way longer than anticipated. But we did cover a lot of ground, and we built everything from scratch. So as a brief summary, we were looking at the GPT-2 and GPT-3 papers. We were looking at how you set up these training runs and all the considerations involved. We wrote everything from scratch, and then we saw that over the duration of either a 2-hour training run or an overnight run, we can actually match the 124 million parameter checkpoints of GPT-2 and GPT-3 to a very large extent. In principle, the code that we wrote would be able to train even bigger models if you have the patience or the computing resources. And so you could potentially think about training some of the bigger checkpoints as well. There are a few remaining issues to address. What's happening with the loss here, which I suspect has to do with the FineWeb EDU data sampling. Why can't we turn on Torch Compile? It currently breaks generation and hellaswag. What's up with that? In the data loader, we should probably be permuting our data when we reach epoch boundaries. So there's a few more issues like that, and I expect to be documenting some of those over time in the Build NanoGPT repository here, which I'm going to be releasing with this video. If you have any questions or would like to talk about anything that we covered, please go to Discussions tab so we can talk here, or please go to Issues or Pull requests, depending on what you'd like to contribute, or also have a look at the Zero to Hero Discord, and I'm going to be hanging out here on NanoGPT. Otherwise, for now, I'm pretty happy about where we got, and I hope you enjoyed the video, and I will see you later.